Hello, and thank you for joining today's MathWorks webinar in this first session, I will discuss trends in research and development for autonomous robots while introducing relevant customer use cases and provide an overview of the applicable MATLAB and Simulink solutions that will be covered in more details in the subsequent sessions. I want to begin by showing an example of a highly advanced humanoid robot. This is Agile Justin, an autonomous humanoid robot developed at DLR, the German Aerospace Research Center. He uses stereo vision cameras to see the world and has special skin that can sense objects. Agile Justin can form a point cloud of the room, such as the table and the pipes, then perform human-like tasks such as connecting the pipes. He can perceive objects such as a person or a thrown ball, and he then plans his tasks such as catching or throwing a ball. Optimization methods for path planning enable him to throw the ball as far as possible. So this was a case of a very advanced robot. Now, let's take a step back and look at the trends toward intelligent industrial robots. Until now, conventional industrial robots have been mainly used, and these robots can be considered automated systems. They execute repetitive tasks throughout the day and night, and the tasks are manually programmed. They're unaware of their surroundings when in operation, so a safety frame is needed to prevent injuries or destroying objects. The conventional industrial robot is efficient as long as operating environments are fixed and makes them effective for executing mundane tasks for prolonged periods. There are many cases of our customers developing these robotic systems. One example is from Ricoh, who used model-based design to design robot actuators, a double motor actuator, which is multi-component and nonlinear. They use physical modeling tools to import 3D CAD data and build high-fidelity models of the complex system. Ricoh engineers were able to build the model in half a day and virtually reproduce the actual hardware characteristics in simulation. In addition is a use case from 3T, who developed a robot emergency braking system for a SCARA assembly using model-based design. They used fixed-point implementations of control algorithms onto FPGA by automatically generating VHDL code. They were able to reduce clean room time from weeks to days, and noted that the time for resolving complex bugs was reduced from weeks and months to only 1 day. Getting back to the trends, in recent days, there are various autonomous technologies being applied to industrial robots. This includes algorithms that allow the robots to be more flexible in their execution, and also advanced algorithms that allow the robot to decide on the task being performed. Also, collaborative robots are robots that work while interacting with humans and are rapidly being developed and adopted due to their agility in adapting to changing work environments. A recent example of customers developing autonomous technologies with MATLAB and Simulink is from Kyocera, who presented at the MATLAB Expo in Japan last year. They used MATLAB, Simulink, additional toolboxes, and MathWorks consulting services to develop grasping and motion planning applications for collaborative robots. Simscape Multibody was used to build physical models for the robot hand, which were used for detailed modeling and simulation to define optimal parameters to successfully grasp various work pieces. They imported the robot model from URDF files using Robotic System Toolbox, provided capabilities to interface with ROS. Though the slides are in Japanese, they are available to view on the MathWorks site. Now, let's take a step forward. Currently, there is a lot of research and development being done for autonomous systems, and these autonomous systems will be largely utilized in future commercial industries. These autonomous systems will be more agile and adapt to complex environments. More complex robots, such as mobile manipulators and humanoids, may become more relevant in the future. These robots will not only be able to execute a large variety of tasks autonomously, but will also cooperate and share intelligence, in other words, data, to optimize and achieve an objective. An example of complex autonomous robot development with MATLAB and Simulink is again Agile Justin from the video shown at the beginning of the session. Agile Justin, developed by DLR, the German Aerospace Center, is a humanoid robot with 53 degrees of freedom, and model-based design with MATLAB and Simulink was used in its development. MATLAB and Simulink was used to develop the advanced control, image calibration, and path planning algorithms, and Stateflow was used to design task sequences such as for grasping or lifting objects. They automatically generated code for HIL, or hardware-in-the-loop testing, and the code was also used for real-time operations. Model-based design helped to drastically reduce the time for implementing complex functionality, while automatic code generation eliminated manual coding errors and allowed the team to focus on designing their complex systems. Now, we discussed the trends in research and development for industrial robots, but in the bigger picture, robots are a portion of the operational process. For example, let's take a look at a smart factory. In a smart factory, the robots are on the factory floor executing tasks potentially in collaboration with human workers. And of course, the data from the robots must be collected, and there is a move towards using local 5G for connectivity and data collection, and this is being researched currently. The data is then sent to the cloud where AI is used to analyze the big data for predictive maintenance or identifying possible process optimizations. There is, of course, a human on the loop which monitors the operational data through OT systems and provides updates as necessary. Now, this is for one factory, but multiple factories will share data in the future, leading to more data collection and opportunities for improved efficiency. Now, MathWorks customers are already developing systems that support this vision. For predictive maintenance, Mondi used MATLAB to develop and deploy operation monitoring and predictive maintenance software, which includes machine learning and allows Mondi to predict machine failures before they occur. Only 6 months were needed to prototype the system, and the production software runs 24 hours a day, 7 days a week, saving more than 50,000 euros a year. Kronos developed a digital twin of their package handling robot using Simulink and SimScape multibody for physical modeling. The digital twin model is used for design optimization, fault testing, and predictive maintenance. Our customers are using MATLAB and Simulink in such ways for developing new robots as well as operational applications. On the topics of IT, OT, and 5G, Shanghai Electric used MATLAB to develop algorithms for distributed energy systems and use MATLAB production server to deploy in a production IT system. Shell India used MATLAB to implement a real-time plant-wide optimization application for a petrochemical plant and worked with MathWorks consulting services to deploy a high-performance application. And finally, Leica Wireless used MATLAB and the 5G toolbox to develop 5G new radio technology, which will enable data rates 10 times faster than LTE, while ensuring that they comply with specifications. You can see that MATLAB and Simulink is used for developing a broad range of new technologies. Now, I want to come back to the autonomous robots and give a simple overview of the development workflow. Now, this will be a brief introduction to some applicable capabilities, but today's upcoming sessions will go into more details for many of the topics. When building autonomous robots, it's difficult and oftentimes high risk to build and test directly with hardware. So engineers ask the questions, how can I model and simulate robots? How can I design autonomous algorithms? And how can I perform integrated tests and deploy to hardware? Well, you could do this with MATLAB and Simulink, which provides a unified development environment for modeling, simulation, testing, and deployment. Let's first look at robot modeling. MATLAB and Simulink provides capabilities to model and simulate your robots at the fidelity level you require. For example, developing brand new robotic systems, you may be interested in the mechanical and electrical components that make up the robot. Physical modeling tools such as Simscape products help to design your systems using physical components such as bodies and joints, as well as various motor types. You can even import from CAD files to accelerate this process. If you're focused more on autonomy, you may not need an extremely detailed robot model. You can use kinematics models such as rigid body trees through a robotics system toolbox. These models allow for faster setup and performance while you focus on developing autonomous algorithms. This topic will be covered in more detail in the next section today. Moving to autonomous algorithm development, perception allows the robot to understand its surrounding. For industrial robots, typically camera or LiDAR sensors are used for this. Deep Learning Toolbox provides capabilities for deep learning, which is often used for computer vision algorithms such as classification and object recognition. Computer Vision Toolbox and LiDAR Toolbox offers capabilities specific to image and point cloud data. For motion planning, industrial robots need to calculate its movements to perform a specific task. To grasp an object, a path is planned, and the robot configuration is calculated to achieve a desired end effector position. Robotic System Toolbox and Navigation Toolbox can be used for motion planning algorithms through forward and inverse kinematics and dynamics, advanced path planners, and even collision checking and detection capabilities. This will be covered in more details in session 3 today. Then, of course, control is needed for execution. For complex applications, scheduling sequences of tasks is often necessary. You can build state transition diagrams or sequence logic using stateflow. Model predictive control can be applied to generate collision-free trajectories. And recently, there has been an increase in research and development for the application of reinforcement learning for robot controllers. This will be the topic of focus on session 4 today. Lastly, testing and deployment. Again, virtual testing or testing through simulation is recommended because it reduces the risk of failures during hardware tests, as it is much more convenient to run large amounts of tests and also reproduce tests in simulation rather than on hardware. Now, ROS is a widely used middleware used in robotics, and ROS Toolbox for MathWorks provides capabilities to connect MATLAB and Simulink to ROS networks and also supports workflows to deploy ROS nodes. Gazebo is a popular ROS-enabled simulator, and you can connect MATLAB and Simulink to Gazebo through ROS using ROS Toolbox, or connect directly for synchronized co-simulation using Robotic System Toolbox. After confirming the proper outcomes of your systems and algorithms in simulation, you can automatically generate code to implement on your robot hardware, whether it's C, C++, VHDL for FPGA, or CUDA for GPU. This will be covered in the last session today. So that was a brief introduction to the workflow for developing autonomous industrial robots. You can use model-based design with MATLAB and Simulink to model and simulate robots, develop autonomous algorithms from perception, motion planning to controls, integrate these components together, and test virtually, and finally, automatically generate the necessary code to deploy to your hardware. As a final use case, I want to share a customer presentation by Yaskawa Electric Corporation from the 2019 MATLAB Expo in Japan. This was for developing a sample application for autonomous manipulator operations. A detailed model of Yaskawa's Moto Mini robot was created using Simscape products, and with this, they can optimize parameters such as for torque costs. An object recognition algorithm was also designed based on YOLO v2, which identifies different workpieces using deep learning while calculating their locations as well. Motion planning was done using Robotic System Toolbox and rigid body trees built from importing URDF files. A speech recognition algorithm, which uses deep learning to understand voice commands, was also included in this project. MATLAB and Simulink was interfaced to Gazebo simulators through ROS Toolbox, allowing for simulations with virtual sensors. In this case, MathWorks products helped in developing various components for this autonomous robot application. Now, as discussed, there are various technologies which make up an autonomous robot. MATLAB and Simulink are the base tools for development, but a variety of optional products are available for developing different types of robots. I briefly introduced some of these tools applicable to industrial robots, such as Robotic System Toolbox and Navigation Toolbox. Also tools for perception, such as Computer Vision Toolbox and LiDAR Toolbox, and other toolboxes as well. Simply put, MathWorks offers tools and capabilities that specifically address the needs for your projects, whether it be manipulators, mobile robots, UAVs, or self-driving cars. As complex robotics become more broadly developed and adopted, MATLAB and Simulink provide a unified environment which allow integrated workflows for developing new robots and their autonomous technologies, not only for simulation, but also allows deployment to hardware as well. I want to finish with some key takeaways for this session. First, autonomous technologies are rapidly being adopted in industrial robots, and this will be accelerated in the future. And MATLAB and Simulink provide an ecosystem of trusted tools that support developing autonomous robots, from modeling and simulation of complex multi-domain systems, developing autonomous algorithms from perception to controls, designing advanced and optimized controls, testing integrated systems virtually and then automatically generating code for hardware deployment. And you can also connect MATLAB and Simulink to the ROS middleware, your ROS networks here. As autonomous robots become more complex, so does the process of developing safe and robust systems. But MathWorks can support you with integrated solutions and technical services to develop and adopt autonomous systems. That concludes this first session. Thank you very much.